And hello, welcome everyone. We are back at this video. So the last video we were trying to sort of describe what's going on if the Prandtl number is very high. Okay, if the Prandtl number is very high within the thermal boundary layer, all these advection terms can kind of just disappear, and it will not have a very big influence on the velocity profile. However, if the Prandtl number is small, very low, then the opposite effect will occur. We cannot just throw these terms away. We'll need to do something. So if the Prandtl number is low, the better way of looking at things is to so-called multiply the Prandtl number throughout. Okay, if the Prandtl number is low, okay, one typical situation where this occurs is in liquid metals. Okay, liquid metals. So like liquid lead, liquid sodium, mercury, whatever. I'm not sure about mercury, but sodium seems to fit that bill very well. Okay, so let's see what happens. So we multiply throughout by the Prandtl number, or rather we don't multiply throughout by the Prandtl number. I'm sorry. We would know that how do we say? Okay, no term is really so-called we cannot disappear all the terms here. Okay, we cannot disappear all the terms here. Yeah, so if Prandtl number is low, we cannot just disappear every single term. Okay, Prandtl number is low, then this thing will be so-called big in comparison to all of these terms here. Okay, again, if Prandtl number is low, this term here would be so-called considered bigger than all of these terms here. But again, we cannot neglect the buoyancy forces, right? We cannot neglect the buoyancy forces, no matter what, because this is a natural convection. It is the dominant effect. Okay, and again, the viscous forces will always play a role in natural convection. Otherwise, the fluid cannot pull adjacent fluid packets, elements, so to speak, not packets, fluid elements upwards. Okay, so what do we do? Okay, well, at least to help in our analysis, if let's say we ever want to so-called make this buoyancy force term disappear, we want a 1 over Prandtl number on this side. If we ever want to make this disappear for very, very, very low Prandtl number, meaning to say the viscosity is so low compared to the thermal diffusivity. Of course, viscosity will be there, but it will not be dominant in comparison to, let's say, the buoyancy forces. Now, so for high Prandtl number fluids, the main driving force, at least in the momentum boundary layer, for bringing the fluid upwards will be the viscous forces. However, over here, while viscous forces are there, the main driving force for bringing the fluid upwards in the momentum boundary layer will not be viscous forces, but rather the advection forces and the buoyancy forces. So this is what I'm trying to say here. We can't really so-called neglect viscous forces altogether, but they are small. We can say they're small in comparison to the advection forces. Okay, am I making sense? I hope I am. Okay, one last explanation. Okay, yeah, all right. In either case, you can't ignore any of the forces, but in the thermal boundary layer, yes, okay, now it's better. In the thermal boundary layer, okay, so we are in the thermal boundary layer. All right, in the thermal boundary layer, we can, okay, let me slow down. Okay, outside the thermal boundary layer, there is no buoyancy. There's no buoyancy. Okay, outside the thermal boundary layer, there is no buoyancy. Okay, Okay, outside the thermal boundary layer, there's no buoyancy. So the only force that's responsible for liquid movement will be the viscous forces. Okay, inside the thermal boundary layer, okay, then we have to take a look at two cases. One is where Prandtl number is very high. Then the dominant force so-called responsible for causing movement is the buoyancy force. Okay, and the main dispersion mechanism for momentum will be viscosity rather than the advection. So that's for high Prandtl number fluids within the thermal boundary layer. That is within here. Okay. Now within thermal boundary layer for liquid metals is a different story. So the main cause of the main driving force will be the what do you call that? The buoyancy forces. The main dispersion mechanism of momentum will be then the advection forces over here. All right. Main driving force is this. Dispersion force will be this rather than viscosity. So this is the way momentum actually spreads throughout the fluid. It's with advection rather than viscosity. So that's what I was trying to say. Okay. So if you forget all of that, this is the important explanation. So we can so-called only within the thermal boundary layer. Okay, that only within thermal boundary layer, advection. Okay, advection for liquid metals or low Prandtl number fluids. Okay, we can neglect momentum transport. Okay, momentum leakage. Momentum, okay, away from thermal boundary layer through viscous action. It's only within the thermal boundary layer for low, So outside the boundary layer, we cannot. Okay, so that's the moral of the story. Okay, so why do I have a Prandtl number on top and Prandtl number at the bottom here? Because we want to see which terms we can neglect. Okay, so we can say this term here is small with respect to these terms here. Okay, right, this term here is small with respect to these terms here. But how then can we make an order of magnitude estimate or comparison between the buoyancy forces and the dispersion forces via advection? Okay. So the way to do it is to make sure there's a Prandtl number in the denominator so that we have a 1 over Prandtl number here. Okay. So the way to do it is to make sure you have a 1 over the Prandtl number here. Maybe I should put this over here. It's way better. Yeah. So yeah. Why am I doing that? Okay. So before we take out this term, we want to see a 1 over Prandtl number here and 1 over Prandtl number here. Okay? 1 over Prandtl number here and 1 over Prandtl number here, so that we know that these terms will not disappear. The buoyancy terms and the advection terms will not disappear. So so these two terms, since they have the same coefficient, we can sort of group them together. And these terms here, without the 1 over Prandtl number coefficient, we can say that because the Prandtl number is so small, this term will disappear. Alright, this term will disappear. So that's why we are doing it this way. Okay, and the so-called important number in this case is slightly different. It is no longer the Rayleigh number, but is a product of the Rayleigh number times the Prandtl number. So there's an alpha square at the bottom rather than a nu and alpha. Okay, so of course, once you take this term out, we can just so-called take the 1 over Prandtl number factor off both sides, and we'll see something different. Okay, so the important number is no longer the Rayleigh number, but something called the Boussinesq number. Boussinesq, the scientist, I mean, he did a lot of work, so I guess a lot of numbers are named after him. A lot of things are named after him for that matter. Boussinesq approximation, Boussinesq number, and even in turbulence his name is there. So he's been working really hard. Well, kudos to him. Okay, so now we can see that in the thermal boundary layer, we can sort of make some terms disappear for different cases, only within the thermal boundary layer. Outside the thermal boundary layer, we cannot. We cannot just lop off the terms. We can lop off the driving force terms because there's no more driving force there. So again, what will the so-called what will the boundary layer look like? Okay, so this is the wall. This is the wall, and this is X. So the let's say here we have temperature, right? Temperature versus X. Okay. Temperature versus X. Okay, so the temperature will just decrease until it stops here. I mean, it's nearly the same as the environment. Okay, that's an initial guess. Then we can sort of guess the thermal bound this is temperature, this is velocity. So this is an initial guess, right? Based on what we were talking about just now. Of course, the temperature will get dispersed as we go along. Okay, so because of no slip, we cannot have movement at the wall. So the maximum velocity will be somewhere over here in the thermal boundary layer. No longer will the maximum velocity so-called be, so no longer will the thermal boundary layer be like so thin compared to the momentum boundary layer. Okay. Okay, so will the so-called will the velocity boundary layer thickness be thicker than the thermal boundary layer thickness, or is it the other way around? Okay, so in general, we do not have, at least if you look at Bijon's textbook, Adrian Bijon's textbook on convection, you'll notice that in his diagrams, the so-called momentum boundary layer thickness, the momentum boundary layer thickness, it will be thinner. Okay, the momentum boundary layer thickness will be thinner than the thermal boundary layer thickness for Prandtl number much lower than 1. Okay, so this is the liquid metal case. I'll probably not touch as much on liquid metals because these are very special cases. Most of the working fluids we have are like oil or if you consider chemicals, oil will be it. If you are in maybe doing heat exchanger, you will be doing with water cooling. The Prandtl number will not be that much smaller than 1. And the Prandtl number will be somewhere closer to 1. Okay, so you may not be able to do this kind of thing. Or you have air. Air has a Prandtl number, I think 0.7, if I'm not wrong. Okay, if I'm wrong, just correct me on that. Okay. But what I want to show you is this important number called the Boussinesq number, which is important for low Prandtl number fluids. So what I'm saying here is that depending on the regime of the flow, your so-called important number will be different. Okay, it will not always be the Rayleigh number, it can be the Boussinesq number. But this is if you are doing liquid metals, which it's pretty in terms of heat transfer, it's a more exotic what do you call that? Heat transfer fluid. You won't always find that in natural convection, unless in very insane extreme cases. For example, I don't know. I'll not name too much. I'm kind of tired right now. I think I need a break soon. So anyway, I'll leave it as that. Low Prandtl number fluids. I'm tired. Okay, so I'm gonna stop now. I'll probably take a break. I'll see you guys next time, where we have pretty much got ourselves to the point where we know what are the terms to keep and what are the terms to throw away. Okay, and of course we can see the importance of Prandtl number in knowing which terms to keep or throw away in certain regimes of flow within this natural convection or within the thermal boundary layer. Alright, so next part before next time you'll try to talk about some solution procedures, I think that's it for now. Thanks for watching.